So when we start considering the reasons why we might have a broadening of a peak, namely why all analytes don't elute at exactly the same time point, and why all molecules of the same analyte don't elute at the exact same time point, we have to start considering a few different terms or a few different aspects to a separation using chromatography. And these terms are all kind of incorporated into what we call the Van Deemter equation. And so this video and the next several are going to walk through each of those terms, the underlying theory behind that term, and then how that term ends up being described in the Van Deemter equation. So the first term that we're going to cover is called term A. It's represented by an A in the Van Deemter equation. And this term has a couple different names. You might see it as the multiple flow paths term or the eddy diffusion term. So where does this particular term come from? So let's consider first a packed column. So remember that a packed column, here's my column here, contains a bunch of particles, and these particles are not going to move during the time of separation, okay? But these particles are all coated in the stationary phase. Okay, so I've got a whole bunch of particles here. So this is my column packing, and all of those particles are, again, covered with the stationary phase. So the mobile phase, let's say, is going to flow from the top to the bottom here of the column as I've drawn it. And so if you look at how an analyte might pass through this particular column, it might take a very direct route, kind of moving between the particles and exiting the column. But that isn't the only route that an analyte can take. An analyte can take a much more windy route. Okay, and you could agree that this is a little bit more windy. Now, if these are both the same analyte, they've simply taken different routes around the column, around the packing in the column, and so they exit the column at different times, right? Because one has to wind its way a little further than the other. So this would exit first because it took a more direct route, and the orange one would exit later. Now remember, I haven't even taken account how it's interacting with the stationary phase. Simply what path does it take as it walks around the particles in the column? So in this case, this multiple paths term is simply looking at the paths that it takes through a packed column are different. Okay. Now here comes a question. If we increase the length of the column, what effect will this have? Well, that means there are more possible paths through the column. There are more particles to walk around. And so a longer column is going to have a higher effect from this path, or from this term, with multiple paths. Other things you can consider is, what if we, instead of having a packed column, what if we had an open tubular column? So this is our packed column versus an open tubular column. And remember that an open tubular column has the stationary phase just kind of coating the exterior walls. Okay. Now here, when an analyte passes through, yes, it's going to have some Brownian motion and kind of move around within the column, but largely it's going to go straight through the column. So because there aren't specific barriers in its path that are going to force it to have different kinds of paths through the column, in an open tubular, term A does not actually apply. Okay, so it doesn't actually apply if we're doing an open tubular column. Now, what happens if we increase the rate of the mobile phase? So instead of moving at one rate, we're just going to go really fast through here. Is this going to actually change the different distances that the analyte will travel? Well, no, it'll just move faster through them. We can think of this like a corn maze, right? You and a buddy are both going through the corn maze and you take different amounts of time. Did it matter if you ran through the corn maze or if you walked through the corn maze? You're still going to have different distances that you both took. And so simply changing the mobile phase does not actually affect the peak broadening because of this term. Now, there are other things going on that the mobile phase will affect, but in this case, the mobile phase flow rate, or the rate at which we're moving this mobile phase through the column, is not going to affect this particular term of the Van Deemter equation. So your book has more information on this particular Van Deemter term, but one of the things that does play a role in how this term affects or is affected and how we can minimize it, just like going from a packed column to an open tubular improved the effect of this term, meaning it made it smaller. Overall, we can say that the particle diameter is going to play a role. So we can write this term, if we were to define it in numerical terms, we have A equals 2 lambda dp, where dp is actually our particle diameter for a packed column. And this 2 lambda, this is a constant. Okay, that's column specific. So in thinking about this, using smaller particles in the packed column is going to minimize this effect and get you a better separation, all the way leading to an open tubular column where we have literally a particle diameter of 0, and this term does not apply. Okay, so this is your summary of the term A, or the multiple flow paths term, also known as the eddy diffusion term. So this is the first term in the Van Deemter equation.